Okay, let us continue. We were discussing the addressing modes. So next we have to start with the instruction set. Okay, so I'll see this. Okay, so guys, before we string addressing mode, given the example. Okay, fine. Anyway, when we discuss the instruction set, we'll understand this instructions again. Each instruction we have to discuss in detail. We'll do that. Okay. So instruction set of 886. I guess before we continue, in this slide, in this PPT file, some details is given about the instruction set before we continue with the actual instruction set discussion. Okay. So an instruction is a binary pattern designed inside a processor to perform a specific function. Okay. The instructions or command is a basically binary pattern. There is nothing but opcode, binary representation of instruction to perform a function or a task. Okay. Operational code, opcode. It stands for operational code. It specifies the type of operation to be performed by the CPU. This is similar to 8051. 8051 also binary number representation, which represents an instruction, is called as opcode, which is easily understood by the processor or controller, which tells the controller or processor what is the task to be executed or what is the operation to be performed. It is the first field in the machine language instruction. Correct. Always the operational code should be the first. So then only processor or controller knows what to do. Okay. So for example, 08 is the opcode for the instruction. So for this instruction move x comma y, there is a operational code represented by the binary numbers. That's called as operational code. So we have already come across operational code in 805 microcontroller. Similar concept in 886 processor. Okay. Operand. We can also say it as a data on which operation should be performed. Operands may be register values or memory values. That is the way we represent the operands, or as a register value, content of register or content of a memory location. The CPU executes the instructions using the information present in this field, that is in the register or the memory location. It may be 8-bit or 16-bit of data. Yes, the thing is, 8051 can handle only 8-bit of data. It cannot handle 16-bit of data. Maybe by splitting into two set of 8 bits. 8086 by default it can handle 16-bit of data. Also, it can split the data into 8-bit to 8-bit data, and it can perform the operation. Okay, so that's possible in case of a processor. Okay, a similar it converts the instruction into sequence of binary bits so that these bits can be read by the processor. The basic purpose of the assembler, there is compiler, what we use generally is to generate the machine code, that is binary numbers, which represents the instruction and the data, so that processor can understand. See, because if you say move A comma B, it will not understand. It doesn't know what is move instruction A comma B. Processor does not understand English. It understands binary numbers, zeros and ones. So for that, conversion job is done by the assembler of a compiler. Mnemonics. These are the symbolic codes for either instructions or commands to perform a particular function. Okay. Yes, for example, move A comma B is a mnemonic. That's called as a mnemonic, which programmer can understand, which is converted into binary bits using the assembler of a compiler. Okay. So what the program we write is assembly code is called as a mnemonics. Basically, like for example, MOV is a mnemonic. It's an instruction, actually it's a keyword, also called as mnemonic. Okay, yeah. So let us start with the discussion on instruction set. So basically, there are let me compare. 6 to 8 instructions. Okay, here I think it is discussed in the next term. So basic instruction set is 6. Okay, string is also mentioned, but in this slide there is additional branch data transfer. Okay, flag manipulation is additional thing. Okay, no issues. We can either discuss this slide. This is also okay. There is a simple example, good examples here. This is also okay. Let us see both. Okay. So there are different ways of classifying the instruction set of a 886 processor. For example, data transfer instructions, arithmetic instructions, logical instructions. Yes, for example, in this slide, in this PPT, what we are watching now is for flag instructions, it is not given separately. For example, string manipulation, process control, and control transfer instruction. In the other one, separate instruction set is given for flag manipulation instruction. Okay, so this basically depends on authors. See, the same instruction set is subdivided into many types of instruction set. That's the basic idea. Okay, so basic classification is data transfer, arithmetic, logical, string manipulation, which is possible in 8086, not in 8051. So process control and what is known as control transfer instructions. Let us see one by one. Data transfer instruction. Okay, basic idea behind the data transfer instruction is to transfer the data from one location to another location in the memory. Instructions that are used to transfer data are addressed into registers or memory location and IO ports. Okay, so that is the basic purpose of what is known as data transfer instructions. Okay, generally involve two operands, source operand and the destination operand of the same size. The both source and destination should be of the same size. Source can include register or a memory location or an immediate data. Source can be an immediate data, correct? We'll take one example, guys. In processor, let us write a simple program. Move AX, 1234H. Yes, you should not write ampersand symbol, okay? Because this is used in 8051. So 1234H means it is data. If you write the same thing within the bracket, square bracket, it becomes a address. Okay, so there's a basic difference. So move AX, 1234H is the instruction which transfers immediate data into register. So immediate data is the source, destination is a register. Both size of both the source and destination should match, similar to 8051. Okay. So destination can be register or a memory location. Destination cannot be the data. This we have seen in 8051 also. Okay, destination cannot be data. It can be a register or a memory location. The size should be either a byte or a word. The size, because it is a 16-bit processor, it cannot exceed 16-bit. It cannot be 18-bit or it cannot be 32-bit. It should be 16-bit. Okay, that's called as byte. 8-bit is byte. 16-bit is a word. 8-bit data can only be moved to 8-bit register or memory, and 16-bit data can be moved to 16-bit register or a memory. That's a limitation anyway. Okay, let us discuss a few data transfer instructions. First, let us use a move instruction. Okay, move instruction will transfer the. For example, let us say one example. What are the possibilities? What are the possibility of data transfer? Okay, move from memory or register. Yes, do we have any question? Okay, move from a memory or a register to another register or a memory. Okay, so example, what are the different possibility? We are moving the data from register to register, or register to memory, or memory to register. Okay, fine. So this is what done. Okay, so compare with the 8051. Okay, in 8051, what is the only possibility is that we can transfer into destination can be a register. Okay, sorry. Just a minute. Okay. Destination can be a register or a memory location. Okay. This, but destination, register or a memory location depends on the source. Depends on the source. For example, let us say this is not possible in 8051. Yes, correct. There is move R0, so R0, R1. Why? Because the condition is both source and destination cannot be registered in 8051. One of them has to be accumulator. Okay. Whereas in 8086, that's not the case. We can directly transfer from one register to another register. It does not require accumulator as the default register in 8086. Okay, because it gives the flexibility of transferring data from register to register. Okay, but what we see is there is no direct data transfer between memory to memory. It is only from memory to register or register to memory or register to register, not from memory to memory. That is not possible in 8051. Okay, that is similar to 8051. In 886 also, there is no data transfer directly from memory to memory, but memory to register is possible. Okay, this is one possibility. Yes, the other possibility is that yes, in this case, in the first case, both source and destination, if it is register or memory. In the second case, the source is a data, because just now we understood that source can include immediate data, immediate addressing mode. In such case, destination can be a register or a memory. It cannot be the data. Okay, so we are transferring data directly to the register or directly to the memory location, immediate data. Okay, the other possibility of data transfer is exchange instruction, for example. So exchange instruction basically can exchange between two registers or between a memory and a register, not between two memory locations. Okay, so that's not again possible. Okay, so directly we cannot transfer the data between two memory locations. Similarly, we cannot exchange the data between two memory locations. There is a limitation in 8086 processor. Okay, fine. Next, let us look into the, of course, we have to discuss push and pop, there is a stack operation. We'll discuss that. Let us look into the instruction. The instruction operation is similar to that of stack operation of 805 microcontroller. Okay. Push the data available in register, 16-bit register or memory location. Okay. Push register, see, when we say push register, the size of the register is 16-bit. Okay, the size of the register is 16-bit. How does it calculate the source location and the destination location? Okay, that is understood here. Okay, let us quickly look into this example. Stack memory, push instruction, push and pop deals with the stack memory. Stack memory is pointed by stack pointer. Okay, since the location, the size of the address is 20-bit, and each location can store 16-bit of data, which is divided into 2 bytes of data. We may be transfer. See, for example, let's say push register. Okay, yes, I'll explain this. Let us understand like this: push register content of a register. Okay, this content of register can be 16-bit or 8-bit or 8-bit. Now, what happens is, when it say, when if the register content is, let us say, if content is equal to 16-bit, then when we use push instruction, push register, okay, the complete 16-bit is transferred into stack memory, okay, and each memory location can store 16-bit of data. Yes, correct. Each memory location can accommodate 16-bit of data, whereas if we transfer, if we use push instruction to push the data, and if the register contains 8-bit data, if the register contains 8-bit data, then the data stored in the stack memory, the stack memory is the 16-bit in size. Okay, there is each location can store 16-bit of data. Okay, but since we are loading, we are pushing only 8-bit of data, it will sorry, it will transfer 8-bit of data to lower byte of byte of lower lower address of stack memory, lower address of stack memory. Let's say, take one example. Let us say the stack memory address is like this. Address is like this. Let us say address, for example, I'll take one example, guys. Let us say 8000H. Okay, so there are two. Let us take the example like this. 80000H location. Okay, so the address size is 20-bit. Okay, now if 16-bit of data is transferred, this 16-bit of data is loaded into this address. Okay, 16-bit is loaded to this address, whereas if 8-bit data is transferred to the memory, stack memory, then what it does is, in this location, 8000H location, which can accommodate 16-bit of data. The 8-bit of data is loaded to the lower byte location of 8000H, because 8000H can accommodate 8 byte location, 2 byte locations, 2 byte data. Out of 2 byte, the 8-bit data which is going to be pushed by the push instruction will be loaded into the lower byte of 8000H location. Yes, okay, fine. Yes, this will understand again. We'll discuss again when we discuss the stack memory. This, let us now continue with the instruction set. So because of this, when you push instruction is executed, the effective address is obtained from stack segment register, which which contains the base address plus stack pointer. There is the location pointed by the stack pointer to which the data is stored. Okay, that gives a physical address or memory address, or memory address. Okay, now this is for the 1 byte of data. For another byte of data, what it has to do is it has to automatically increment by 1. The address has to be automatically incremented by 1, so that it can store another byte of data or another word of data. Okay, but the stack pointer decrements by 2, so that it goes to 2 locations. Yes, okay, this, don't worry about this. I'll discuss this concept in detail again. Okay, so for timing, you understand that push instruction is used to transfer the data available in register or memory location on top of stack memory. Okay, this I'll discuss again. Possibly in the next class, I'll take up this stack memory discussion. Okay, yes, what is the difference when it comes to memory address? So memory address, if it is a source is a memory address, then it's similar to the same operation, stack segment register plus stack pointer, which gives the effective address. Okay, register is also as a address, memory location also as a address. Okay, so basically, the see, only difference between these two is that the content is available in this case a register location. Here in this case it's a memory location, but how the processor access the stack memory operations remains the same for both the register as a source of data or memory as a source of data. There is not much of a difference. Okay, but the only thing is either it's going to take the data from register or a memory based on whether we specify registers or memory. Okay, fine. Yes, what about pop instruction? Is similar to 8051. It will retrieve the data from the top of stack memory and loads it into register or a memory location. So if it is a register location, so then effective address is calculated from stack segment register plus stack pointer, from to which the stack pointer is pointing to the data on the stack memory. That gives the effective address. That from that effective address, physical address is calculated by adding the stack pointer address to stack segment register. There is base address for stack memory, and the 2 bytes are copied into 16-bit register. What is this 2 byte? I'll discuss, guys. These concepts I'll discuss again in stack memory. So for timing, you understand that push is used to store the data onto the top of stack memory. Pop is used to retrieve the data from the top of stack memory. Okay, we'll discuss this again. Okay, yes, we have this in-out instruction. Okay, so there is a separate instruction for port data transfer. Yes, see, in 8051 we don't have a separate instruction. Let us say, for example, ports, we need to send some data through port 0. Okay, so we need to send some data through port 0. Okay, let us say the data is 08H. Okay, yes, how do we do this, guys? How do we transfer this data in 8051 microcontroller? In 8051 microcontroller is very simple. Okay, so transfer the data. I need to send 08 through port 0. Move port 0, comma #08H in 8051 microcontroller. Very simple. Okay, that is move instruction is used to transfer data. Either it's a port location, or it is internal memory location, or it is a register location. Okay, for any, say for example, I can do this also. Move 30H, comma #08H. Okay, so in this case 30H is the memory address. This I'm talking about 8051. Okay, so I want to compare between 8051 and 8086 in the port data transfer instructions. So port P0 is a port 0, 30H is a memory location, and let's say move R0, comma #08H. See, either it is a port address, memory location, or a register. Instruction is always same. That is move instruction. Okay, that is not the case in 8086 processor. Okay, in 8086 processor for IO operations we have a separate instructions called as in and out. Let us understand this instruction in. Okay, so for the data transfer, there is the port through a port. Okay, we have to copy into AX register, which is obtained using destination segment register, sorry, data segment register, which is specified using DX register. Okay, because we know that DX register is a data segment, is a segment register for for the data segment memory area. Okay, this we have four registers: AX, BX, CX, and DX. For in-out operations, we use DX register as default. Okay, so if you want to send some data through a port, its address has to be specified as part of the DX register. And if you use a bracket, what is the microprocessor does is it will take the data loaded in the location whose address is stored in the DX register. From that address, the data is loaded into EX register. Okay. So thereby, what happens in case of port address is that, okay, so the content of AX acts as a address. So from that address, data is copied into AX register. So when we say AX register, the size of AX register is 16-bit. So thereby, it copies. Yes, just a minute. There's a power cut here. Okay, power is back. So otherwise there will be issue with the network. Okay, I hope. Okay, things are okay. Things are seems to be okay. So the data copied from the memory location, whose address is stored in DX, transferred into AX register as byte as a byte of. See, if it's 8-bit data, it will be transferred into lower byte. If it is 16-bit data, it will be transferred into AX register. So that is the meaning of this instruction. Okay, yes, this is one method. The other method is if I use the direct addressing mode, that is address part of the instruction. Okay, in such case what happens is address, from this address data is transferred into AL if it is 8-bit data transfer, or it is AX if it is 16-bit data transfer. Okay, so this is you using in operation, that is to read the data from the memory. Okay. Similarly, to send the data through the memory, through the port, we use out instruction. Yes, again, I think there's a yes, there is a port fluctuation here. I'm in the college. There's a port fluctuation, so that's why you may experience some discontinuity in the session. Okay, that may be the reason. Okay, yes, to send the data through the port, we use the out instruction, same operation. Okay, but in this case, the destination is represented by is destination represents the port address. Yes, in this case, the source is represents a port address as DX. Out instruction, destination is represented using DX register. Source is AX register. 8-bit of data to be transferred through a port, AL register is used, 8-bit register. 16-bit of data to be transferred, AX register is used. Okay, along with the out register. Okay, so we can use two methods. One is using DX register, that is using a base address method, or directly the address of the port. We can do both the operation. All this is possible. So this is using in and out instructions. Okay. Okay. Yes. Next is arithmetic instructions. Okay. So we'll discuss example for all of them. But let me check with this slide. If we have any examples, we can. Okay. This is a simple move example for a move instruction. I think we saw the example for a move instruction. Okay. So the data transfer can be anywhere from the source of data can be immediate data, or it is the stored in address. Address is part of the instruction direct addressing mode, and it is from register to register. Okay. So this is explained here, guys. Before in execution, after execution, what is the data loaded? Okay, this is fine. stack operation, stack pointer, push instruction. Example, push operation, the air byte is pushed first out of yes, in the stack operation there is, when we discussed, there is uh, yes, just a minute, I'll go back to this slide. There is push and pop. Okay, in this slide the detail is given. Okay, for stack operation, 16-bit register circuit contains the address of the data item concurrently on top of the stack. Okay, stack operation includes pushing data onto the stack memory or popping the data. We saw this. Stack in 8086 is a last in first out type of memory, which is similar to that of 8051 microcontroller. Okay, this we'll see one example. Source can be a register or segment register or a memory for a push instruction. Okay, we'll see one some example. The instruction pushes the contents of the specified source onto the stack memory. In this, stack pointer is decremented by 2. Why it is 2? Because in this example also we saw stack pointer being decremented by 2 in the previous slide. Stack pointer being decremented by 2. Okay, why it is 2 is because while storing the data, the air byte of data is pushed first. Okay, yes, just now as I was explaining. Okay, let's change the data. Okay, fine. Okay, so the data size is 16-bit. Okay, first it will not transfer 16-bit data at the same time. First it will transfer upper 8-bit of data is transferred first onto the top of stack memory. Stack pointer decrements by one value. Then the lower byte is transferred. The stack pointer is decremented by one more value, one by one value. So effective stack pointer variation is stack pointer minus 2. In 8051, stack pointer is always decremented by 1 or incremented by 1 because it can handle only 8-bit of data. 8086 can handle 16-bit of data. So if the source data is 16-bit in size, first it will load upper 8-bit of 16-bit of data onto the stack memory. Then it will load the lower byte onto the top of stack memory. Okay. So thereby effective operation on stack pointer is minus 2 because it points to the two locations. Okay, fine. This example is push AX. There is okay. Push the content of AX register. Yes, what is the size of AX register? Is AX is 16-bit. Okay, out of 16-bit, AL is the lower byte, AH is the upper byte. First, the AH is transferred onto the stack memory. Stack pointer is decremented by 1. Then AH is pushed onto the stack memory and stack pointer is decremented by 1. Okay, this in the next class I'll discuss the memory operation. I think here we have. Okay, so this will discuss in the next class, of course, in detail, so that we'll understand. If possible, let us look into this now. Okay, I think I have 10 minutes left. Let us look into this. Okay, so let us understand this operation. So examples are push AX. The size of AX is 16-bit. Similarly, push DS. Yes, what is AX register? Is it is a normal register. DS is a data segment register. So source can be a register or a data segment register, or it can be a memory location. Push 5000H within the bracket indicates it's a memory location. All these three are. Push instruction cannot take data as a argument. Data cannot be specified as a push instruction. Okay. So initial positions are like this. Let us try to understand this diagram. Stack pointer is pointing to a particular location in the memory. Okay. So when we use the push operation, decrement stack pointer and store there. When we use the push operation, what does the microprocessor does is it decrements stack pointer by it decrements the stack pointer by one value, stores the higher byte. Let's observe here. It decrements stack pointer. Yes, what do you mean by increment and decrement? Okay. Yes, in 8051. Okay, let us understand the memory like this. For example, in first let us understand 8051 address. How do we specify the address? Is higher address first, FFH. This is the address of a ROM space. Address of a ROM space. Okay. From FFH to the lowest address is okay 0000H 0000H. Okay. If you go from 0000 to FFH, we say that it is a increment in address. Increment in address. Okay. Whereas if you go from FF to 00, we say that it is decrement in address. With this context, Stack memory in 8051 always go from lower address to higher address. So thereby, stack memory, when we perform push operation, stack pointer always increments by one value in case of 8051. Whereas in case of 886 processor, please let me go back here. In case of 8086, what happens is the stack memory, let me write the address guys, FF FF, oh, sorry, FF, because the address size is 20 bit in case of a 8086 processor. Okay. Now the address lowest address is 00000H. In case of 8086 processor, the stack memory grows downwards. That is, stack memory goes from higher address to lower address. Whereas in 8051, stack memory goes from lower address to higher address. So thereby, in 8051, whenever we use push instruction, stack pointer is incremented by one value, then the data is stored. Whereas in 8086, since the stack memory grows downwards means from higher address to lower address, what happens in case of 8086 is that stack pointer is decremented by one value, then the data is stored. Okay. How many times it is decremented? See, in 8051, how many times it is incremented or decremented? Only one times, because the size of data is always 8 bit. Okay. Whereas in this case, if the size of data is 8 bit, stack pointer is decremented by one value. Whereas if the size of data is 16 bit, then first upper byte is transferred first. Okay, then stack pointer. Okay, let me write that again. Upper byte means upper 16 bit. Okay. Upper byte. Yes, I'm sorry. Upper byte is loaded first into the memory. Upper byte is transferred to the stack memory first. Upper byte is loaded first. Stack pointer is decremented by one value. Okay. Then what does it do is it will copy the lower byte. Lower byte is loaded to the stack memory, and again stack pointer is decremented by one value. Okay. Effectively, if the data size is 16 bit, stack pointer is decremented by how many times guys? Stack pointer is decremented by 2 times if the data is 16 bit. Whereas if the data is only 8 bit, stack pointer is decremented by only one value. Okay. So this is the operation performed in 8086 processor. Okay, that is the difference between 805 and 8086 processor. Let us look into the instruction. That's why stack pointer is decrementing, because we are going from lower address to higher address. This in this slide the address is not specified, but you understand that we are going from higher address to lower address. That's why the stack pointer decrements by one value. First higher byte is loaded, then again stack pointer decrements by another value, lower byte is loaded. Stack pointer decrements now to point to the location in the memory, empty space, where the data can be stored in the next instance when we execute the push instruction again. This let us understand using this instruction guys. Let us say, for example, I need to load the value. Stack pointer is now pointing to 2002 its location. Okay, there is location pointed by stack pointer is 2002 location. Okay, now when we use push instruction. Okay, so let us say ch content of ch is 10 and cl is 50, for example. Okay, now I'm transferring the content of ch, that is ch and cl, onto the stack memory. What happens is that initially 2000 location is empty because it is pointed by stack pointer. When push instruction is used, stack pointer is decremented by one value, that is sp minus 1. It becomes from 2002 to 2001. Yes, there is a chart. Oh, this what time? Okay. Yes. Okay. Fine. Okay. Yes. I'm sorry. I didn't knew that you have a class at 12. Okay. Yes. I'll continue in the next class. Thanks for joining. See you. See you in the next class. Bye. Okay. Bye. Bye. Take care. Bye. I'll continue in the next class. No problem. Bye. See you.